What are you doing at the beginning of the semester? Such a waste of space.
All right, here we go. You've seen this slide before, but it is important to understand how these are different. Okay, capacitor and inductor, when charging, they behave oppositely. Okay, um, at the beginning, a capacitor uh, acts like a wire. There is no voltage drop across it. It takes no energy. It's like I'm an empty plate. Come on in. Let's woo. Yeah, all right. But then as that gets filled up, it's like, oh man, we're getting crowded. Oh, we're getting crowded. Oh, what are we doing? And eventually, um, it behaves like a broken wire. You have as the charge increases, so does the voltage. The voltage um, across that behaves in a similar manner, and the current drops off in exponential decay. The voltage across this one does the same thing, drops off. It starts strong, it takes all of it. The voltage across the battery is equal to voltage across the resistor, and over time it behaves like that. Okay? With an RL circuit, the inductor is the opposite of that. Initially, the inductor hates a change in current. It's like, what are you doing? What is this going? And so it's like, no. And so it resists a whole lot. And so all the voltage across initially is across the inductor, and none across the resistor because there's no current at the beginning. As time goes on, um, that voltage drop across it gets okay with the change. Like, all right, all right. And eventually, there is no change in current, and so it's a steady state. There is no voltage drop, and it acts like a wire. At the beginning, it acts like a broken wire, and the current starts at zero and eventually goes to some steady state. So the voltage drop across this initially is zero and behaves like this across the resistor. How are we doing with that? Okay, Jared.
They never actually meet those numbers, though, right?
I mean, it's an asymptote, so like from an engineering point of view, absolutely. From a math point of view, no. Okay, like you're never going to get a meter that's going to read, nope, not there yet. It's going to round up. Okay. Now, discharging, they act the same because there's now energy stored in the electric field. There's energy stored in the magnetic field. And so when you disconnect them from a battery, they become a temporary voltage source. And so there's voltage drop and current drops for both of them. Good with that? So, what happens if you stick them together? What? Okay, so this is called an LC circuit. So, what we're going to start with is a charged capacitor. Okay, so there's a voltage across this. And so when you connect the switch, there's motivation for these guys to come, the electrons to come off over here. But the inductor's like, whoa, 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 whoa. Like, what? And so it fights it. Does that make sense? Okay. Whoa, 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 whoa. And it fights it. Okay. So the analogy is it's like a mass and spring oscillator system. Okay. So initially we have, here's our equilibrium point. We've stretched it. There's potential energy stored in the spring. Okay. There's electric potential energy stored in the capacitor. Okay. So then the you let it go, and so um, positively charged flows. This electrons go, all right. So this is like creates a change in magnetic field. It's like okay, and so here the mechanical energy is in kinetic energy. The energy here is stored in the magnetic field. Okay, and it's like it pushes through, and it's like okay, we're going. It's like okay, let's keep doing this. Okay, and then um, the it keeps pushing it, and so it charges the capacitor again, and this is like the spring being compressed on the other side of the equilibrium point. And so, and then it shoves it back again, like go, and it's like, ah! And so this, it's like, all right, so we keep on pushing it, keep going, kids, keep going, and like it charges that capacitor, and it oscillates. Yeah.
Did you remember your coffee this morning?
I didn't. I'm just pumped because we're like, we've got limited time. Um, so this, so the question of like, is it conservative? If there's no resistance in the wire, but there's resistance in the wire. So no, but yes.
I'm swamped. Just get Grammarly. It's free. Can it help with what I wrote last night?
No way, man.
If you connect the charged capacitor across an inductor, you will see a beautiful energy exchange take place between the two elements. These energy oscillations look as if the capacitor is saying, you take the energy, and the inductor then says, no, you take my energy. Why don't any of these elements store the energy and become settled? Let's have a look at the interesting physics behind these oscillations and some of the applications. Before diving into the LC circuit, we need to understand a simple circuit, a capacitor-resistor circuit. The capacitor is fully charged initially. Let's introduce a resistor into the circuit. Here you can observe that initially the current flow is at the maximum and then it sharply decays with time. This is expected because at the beginning, the charge difference is at the maximum, so the current has to be at the maximum. Now let's see what will happen if the resistor is replaced with an inductor. Here again, the capacitor is fully charged initially. It's quite logical to expect that there will be a huge current flow at the beginning, and then the current flow would reduce as in the previous case. However, this will not happen in practice. An inductor develops EMF across it, based on the change in current flow. This means that a drastic change in current is not possible across the inductor, as in the previous case. Now the current flow starts from zero and increases to the maximum, and then comes back to zero again. In an inductor-capacitor circuit, the current flow variation has to be gradual, and here we can see that the current flow in the LC circuit is shaped like a sine curve. Let's look at the electron flow animation once again. The current in the circuit starts from zero and gradually achieves the max.
Okay. Kirchhoff's loop rule is still a thing. Okay. Here you have a voltage gain has to equal voltage drop. Okay, this is pushing hard, this is pushing back against it. Like, I don't want to change. Does that make sense?
Maximum value.
Oh, stop.
In the next 1/4 of a time period, the current from the capacitor starts to decrease, resulting
boo hiss. Okay. All right.
in another change in current. At the end of the capacitor discharge.
Oh yeah, boo hiss. So right here, the capacitor is uncharged momentarily. There is no voltage drop across there, nor is there voltage drop across this one because it's like kind of a steady state. The rate of change of current that's like a maximum. Like the derivative of that is 0. Does that make sense? But the inductor wants to continue that. Like, hey, it's like the inertia thing. And so it continues, but then it starts to decrease.
Discharge,
And so
if
you
you
get a
check
voltage
the EMF
drop.
across the inductor, it will have the opposite polarity to the initial EMF. This reverse EMF charges the capacitor with the opposite polarity. In the next half of the time period, the capacitor will be fully charged with the reverse polarity. This also means that the current flow will be in the reverse direction for the next half. Hence, in an ideal circuit, this back and forth flow of current would continue to charge and discharge the capacitor and form endless oscillations of energy. However, practically, we can never achieve such ideal behavior due to the presence of resistance. The resistance causes energy decay in the form of heat. This means that in a practical circuit, the oscillations will die out eventually. As we increase the resistance, the oscillations die out very quickly, as shown. If we increase the resistance further to some critical value, there would be no oscillation at all. Underdamped LC circuits have many applications in industry, namely thyristors, magnetrons, etc. In communication systems, they are an integral part of frequency filters. Please don't forget to support us.
We know what those are.
Okay.
I always wondered how my thyristor worked.
All right. So, okay. So, it's sinusoidal. Go to that. And so the time derivative of charge is current. Okay, so here we'll say you have a cosine graph, take the derivative of that, you get a sine. Derivative of cosine, isn't that negative sine?
No, I thought it was tangent.
We're gonna go with this, okay? And so this is, I think that's on your equation sheet. That's on your equation sheet. So this is the angular frequency, how quickly you're going through a cycle. So this is like 2 pi complete cycle over the period. Good with that? Okay. So if we, let's see, do I want to dive into that yet? Okay, we're going to hold off on that. Okay, so here you get energy bar graphs. Okay, initially it's all in the capacitor, none in the magnetic field. Sorry, it's all in the electric field, none in the magnetic field. At this point in time, it's all in the magnetic field, none in the capacitor, and it just flip-flops between the two. Okay, good with that? And this would be when you're back to here, that would be a complete period. Does that make sense? Okay, so making that connection between the mass spring and the inductor capacitor circuit, your inductor acts like kinetic energy, your potential energy acts like the spring potential energy acts like the stored energy in capacitor. So at any moment in time, you have this this would be like your maximum amplitude, and at any moment in time it's split between your kinetic energy and your potential energy. Here you've got the same idea. At any moment in time it's split between these two. This would be fully charged. Okay. I would not worry about that.
The two on the top with the magnetic and electrical energy, are we given that in the equation sheet?
No, yes, you are. That and yeah, you gotta scroll a lot. Yes, you are given you're given that one straight away. This one looks like this. Yeah, that one looks like that on the equation sheet. Good. So, a charged capacitor is connected to an ideal insulator to form an LC circuit. At time 0, the capacitor is fully charged, has a capacitance of 100 microfarads. The inductor has an inductance of 100 henries. At a given instant later, the charge on the capacitor is measured to be 3 microcoulombs, and current is equal to 75 microamps. What is the maximum charge on the capacitor? Okay, so what we're going to employ is conservation of energy here. Okay, so initially, so not to confuse it with electric field, I'm going to say total energy. I don't know, whatever, energy. Maybe I'll just write this. That isn't. Energy equals energy. Okay, so it starts fully charged. So we know that that is equal to 1/2 charge times voltage. This is what they give you on the equation sheet. So this is fully charged capacitor. And then over time, that amount of energy is split between them. And we know that this is the energy. You know, I should do this. The energy of capacitor initial, and then energy of capacitor final plus energy of inductor final at some time. This gets ugly. I don't know what to write for changing. Okay, this isn't helpful because my voltage is changing. So I'm trying to pretend like you don't have this memorized and you're looking at the equation sheet. You've got this other equation. Okay, we're going to substitute in for voltage. So voltage is equal to charge over capacitance. So this is going to be 1/2 charge times charge over capacitance, and that is 1/2 charge times Q over capacitance. lowercase q and lowercase I mean it's a changing amount. Capacitance doesn't change. James.
Why do we not just say that we're doing it when the current's maximum is a charge minimum and just have L big I and no Q delta V in the final?
Because we don't know the maximum current. We could, if you knew the maximum current. Okay. So here we have Q squared over C, 1/2 Q squared over C plus 1/2 L. Oh, that's a. And we have everything except for capital Q. Good with that? Jared. The value of capital C is nope. Yep. That's a defined, like the inductance. So this is your capacitance, and this is your inductance. Good with that?
Do we have to convert all of our micros to regular?
Yes, convert all your micros. Yeah, because you're adding things. If it was just multiplying, you could get away with it. Good? Okay. So we use these inductor circuits. Sorry, not these inductors. We use these LC circuits to help distinguish different frequencies used in different cell phones. Every cell phone has a certain frequency associated with it. Okay. Oh, look at me. So nice of me. Actually, let's talk conceptually why this happens. So this is how frequently it oscillates back and forth. Okay. As you increase the capacitance, this is a bigger bucket, and it's going to take longer for that bucket to fill. Okay, so as this goes up, this goes down because it doesn't happen as frequently. As your inductance goes up, that's more inertia saying keep doing what you're doing, and it takes longer to switch that. So as this goes up, this goes down. It happens less frequently. You all right with that? Okay, all right. Correct answer is, tell your neighbor.
It should be about. It's not gonna be, but it's not gonna be more than. Yeah, so it's not gonna be that.
Correct answer is it going to go up or down? Oh, find someone you disagree with.
Right, yep, it's gonna be neither.
Is that twice as much distance between the capacity and the
What? What?
Are they like all the same capacity?
Yeah. Yeah.
Why is there more distance between the bottom and I don't like that.
Correct answer is D, dangerous dinosaurs. You add capacitors in series that decreases the capacitance. 1 over C plus 1 over C. Good? Correct answer is A. As the gap distance increases, capacitance goes down. As capacitance goes down, this goes up.
Yeah, I just said E. Because my brain went, what?
Big is small is big is small is double. B. You gotta go.
Recognize, we're looking for the time. What do we say? Twice the time. Because it halves the frequency. Halves the frequency, doubles the time. Frequency and period are inverse. Yes? Okay.
Yeah, that's what I'm saying. So C is the negative G.
Okay, have a conversation. I'm probably going to need to intercept this one, but go for it.
Oh wow. You can't see the negatives of each other. it's proportional to speed direct versus I think is going to be like
It is at least.
It's also more so to the current. So,
I see all of them are. Wait a minute, you talk because it's a sign.
Okay, what do you say? All right, potential difference. We're looking at loop rule. There's only voltage gain, voltage, okay, but they have to equal each other. Does that make sense? Okay, so this is charge over capacitance. Yes? And this is L di over dt. Yes? Di dt, this is the second derivative of charge because current equals dq over dt. Yes? Okay, does that make sense? Good? All right, so the video is getting to this. So if you have resistance, this is, I think this is beyond the scope of the class, but here's, if they pose this to you, it has the same frequency. It's just the amplitude's getting smaller. Okay? So heat, energy is being lost due to resistance due to heat. Okay? These are beyond, yeah. Okay? So, how does your stoplight know when this change, like there's stoplights are triggered by something, right? Some of them, some better ones, okay? If you've ever noticed like cuttings in the road before, they stick coils of wire in the road. And so there's current flowing through here. When you drive over that, then the fact that you've got iron in like steel of your car, the frame of that changes the flux in that loop, that changes the magnetic field strength. And so that sends a different current, an induction to the box saying, hey, there's a car there. Some motorcycles actually buy strong magnets to stick under their frame because they don't have enough iron to like to like signal the thing like, hey, I'm sitting here.
Do the ones in the bike lane work the same way?
No.
What if you're
Oh, I don't know.
fiber bike or something?
Yeah, you're toast. It's not weight. I used to get out when I was in high school. Come on. That doesn't work. I didn't know. I didn't know it was below that. I was like, maybe they stick a little.
I really just thought you were some crazy guy jumping.
Yeah. Okay. All right. Don't take notes on this. Okay. Okay. Mutual inductance. The idea of this is when the changing magnetic field of this interferes or like goes through this and changes, this guy experiences a change in flux because of this one. That's mutual. Everything we've done so far is self-inductance. Inductors are self-inductance. Okay, this is how the theory behind it, how a transformer works. But you don't need to know this depth. Just kind of throwing this out here. Okay, so these are solenoids, like ultimately the solenoids with magnetic field going through it, and the flux is changing. James.
What do we need to know this conceptually?
Yes. So just like I'm trying to hit it to you conceptually. So these are pieces that you know inductors, okay? And there's flux going through there, like that's a thing. You were introduced to this idea of transformers last year, and I touched on it a little bit this year as well. So it's the inductance is based upon the rate of change of the current in the first loop compared to the inductance of the second loop. This M is L, what we would consider L, but it's M for mutual inductance rather than self-inductance. And so what happens is this ratio of the flux to the number of coils times the flux going through one coil over the current and the other one has a flip-flopped. And it turns out that the inductance for mutual inductance is mutual. It's the same. Okay, and this is how transformers work. This is where that comes from. Okay. So you can get arrangements like this. Okay, and this is actually how a ignition switch is wired in your car. A 12-volt battery can make a spark, which is like thousands of volts are required to make a spark, like a spark plug too. So off a 12-volt battery, you're never going to get a spark that much off of a 12-volt battery, unless you do some crazy cool transformer stuff. Okay. So this is Lenz's law. Okay. Yeah. Call that good. I'll do that.
My work is easy because I use ClickUp. Here's how I keep track of all my tasks. I start by brain dumping everything I need to get done.
So catchy. Synthesizer action.
Conventional automobiles burn gasoline in an internal combustion engine and convert that energy into motion. But first a spark is needed to ignite the fuel mixture. This demonstration shows how a 12-volt battery generates the high voltage required to create such a discharge. The heart of a car's ignition system is its ignition coil. This coil is a kind of transformer, a device that transfers voltage from one circuit to another, either as a lower voltage, or in the case of the ignition coil, as a higher voltage. It does this by creating a changing magnetic field that induces a current in a conductor exposed to that field, a principle known as electromagnetic induction. Like other transformers, An ignition coil consists in part of two coils of wire, both wrapped around the same iron core. The inner or secondary coil has far more turns of wire than the primary or outer coil, making this a step-up transformer that will convert the battery's 12 volts into some 40,000 volts of electricity. First, we will close the knife switch to create a circuit that includes the battery and the induction coil. Although electrons move from negative to positive, the convention is to think of electrical current as moving from positive to negative, so that's how we'll show it here. As current flows to the primary coil, a magnetic field gradually builds up around it, as well as around the secondary coil housed inside. If we open the knife switch to stop the current, the magnetic field suddenly collapses. Due to the principle of electromagnetic induction, this rapid change induces a surge of...
Okay, it's the rapid change. Someone asked when you're doing the inductor thing, is it possible to generate a greater voltage than what the power supply was giving? Does that make sense? Like greater than the battery? Absolutely. It depends on how quickly that was changing. Does that make sense?
Current in the secondary coil, which streams out and jumps the spark gap in the circuit. There is something else happening when the knife switch is opened. Let's watch again. This time, keep your eyes on the capacitor, two plates separated by an insulator. When the knife switch opens and the field around the coil collapses, the collapsing field around the primary coil induces a surge of current called back EMF in the primary coil. This unwanted surge of electricity travels back toward the switch. The job of the capacitor, called a condenser in auto ignition systems, is to safely absorb the back EMF and prevent the surge from reaching the switch and creating a damaging spark across those points.
Cool. So some electrical panels have a big capacitor in there, and that's protection. That's like a surge protector. For in case there's like this back surge somewhere from like a lightning strike or just random weird stuff. So they throw capacitors in there as like a buffer, a protection against that stuff. Cool. All right.